Okay, first of all, thanks for the organizers for allowing me to present the work with my collaborators and doing it presently here physically. So this is work that I did with my group of collaborators from the IAC. It's about the dynamical interaction of Coma Berenices open cluster and the GroupX moving group. And you will see that some of the comments that were previously said about determination of open clusters and the superstructure will be shown here as well. We have same issues. These are preliminary results on based on Gaia EDR3 and some combinations with other public surveys and our own radar velocity measurements. The preliminary results are basically on the membership, the spatial velocity, and mass distributions. So a brief introduction. Can I move this thing from here? I don't know. Okay. So Coma Berenices is an open cluster, the second closest to the sun. It has more than 200 members, and it's an age with it has been characterized with isochrones and lithium depletion boundary between 500 and 800 million years. It contains several substellar objects, L dwarfs, have been widely studied from the original paper from Trumpler 1938 to date, and Gaia revealed some very interesting structures, like the tidal tails that were discovered by Frunkrantz and collaborators, and also by Tang and collaborators. So GroupX was also discovered thanks to Gaia DR2 data by Frunkrantz, the same in the same paper of 2019. It's very close to Coma Ver, with within 65 parsecs, has more than 100 members. It's relatively younger than Coma Ver, so we don't expect a common origin. It's about 200 to 400 million years, according to isochrone ages and geochronology. And interestingly, it was proposed to be composed of two substructures simultaneously by Tang and collaborators and Frunkrantz. And also Tang collaborators also mentioned that it's a possibly disrupting cluster, or disrupting stellar system. So here I'm reproducing some figures from Frunkrantz, where it's the XY coordinates and the barycentric positions of GroupX members. You can already see some substructure here. The Coma Ver cluster, the core of the cluster, and some of the tails members, or members in the tails, sorry. And the shaded region represents some of where the expected tails should be located. We already see this. There are some members in this region that are you can see the cursor, yes, that are interacting. So this is an example of interacting open cluster pairs that already known in the literature, and they have been predicted, and theoretically their fractions are supposed to be between 8% and 20%. However, the observational constraints show that the fractions are lower. Subiran and collaborators identified only 11 open cluster pairs within their sample of high quality open clusters, which represents it's a lower limit because the sample is not complete, but it's a lower limit of 2%. Very recently, using Gaia EDR3, Piatti and collaborators also found that IC4665 and Collider 350 are probably open cluster are colliding. And well, this work on Coma Ver and GroupX that was originally proposed by Frunkrantz, that these two systems are colliding and will collide within a few million years. So this is the introduction. So we started analyzing Coma Ver because we wanted to characterize the lithium depletion boundary age of this system, as well as for GroupX. So we start searching in Gaia data for the very faint members. And we realized that the membership methodologies that were currently developed were struggling to identify these very faint members at the bottom of the Gaia limit. So we applied several techniques, and then we decided to well, how can I move to the arrow? It's frozen, or okay, so it's okay. Thanks. So this is a kind of a summary of membership methods for open clusters. Of course, it's not exhaustive. I know that some of you have your own methods, and it's only to exemplify the kind of typical methods that we have for open clusters and the problematics that we have in the case of Coma Berenices and GroupX. So in general, there are two types of methods. There are non-parametric methods. Basically, the simple example is a kernel density estimate, and parametric methods, which basically we infer the parameters of the cluster or the parameters of some models. And there are what I say 3 generations of open cluster methods, membership methods. Sorry. The first generations were basically doing some cuts in some observable space, like in the photometry when we didn't have proper motions, or the convergent point method, which still needs some hard cuts on the distance between around the cluster. And these methods usually didn't take into account, well, they make a hard classification. It was not probabilistic classification. And the second generation of open cluster methods, which included Upmask, Banyan, and the work of Sarro and collaborators, did this. They created a model for the field, a model for the cluster, then computed membership probabilities and disentangled the populations with a probabilistic taking a cut in membership probability rather than in some subspaces of the observables. And the third generation was recently created to deal with this problem of substructures in open clusters, and for example, dealing to try to identify the tails. This work, for example, there is this method from the Vienna group, which is kind of an extension of the convergent point method that they developed to identify the tails. There was this paper from Mangast and collaborators on the tails of several open clusters in the solar neighborhood. There is a StarGo, which is a non-parametric method. It's based on a neural network that is constructed on the physical space, this neural network, and then this neural network is used to classify sources on the observed space. So in general, these two methods, the convergent point from the Vienna group and StarGo, do this. They do a machine learning technique in the physical space, and then to transform their observables, their Gaia observables to the physical space, they need to apply some quality cuts, basically this parallax error of 10%. And then they need, for example, sources with radial velocities, which is, is not the case always. And then when we apply these kind of methods, we see that we don't reach the very faint limit of Gaia, the photometric limit of Gaia, because their uncertainties, particularly in parallax, are very large. So we decided to develop our own methods. And so I think I need to go faster. So basically what we do is we created a second version of this Bayesian hierarchical model that was designed to simultaneously infer the parameters of the cluster and the parameters of the stars. The first version was designed only to measure distances of stars in open clusters and the sizes of the open clusters. And the second version now is based to infer the phase space positions and the parameters of the cluster in the phase space. So we work with astrometry and radial velocities, possibly missing radial velocities from Gaia. And it's very simple in the sense that the model is Gaussian or a combination of Gaussians. The method is Hamiltonian Monte Carlo. We need this type of method to infer thousands of parameters from the stars on the cluster. And then one of the advantages that it takes into account and corrects for the parallax spatial correlations that we see are present in Gaia data. And well, one of the advantages, it works with sources with missing values in radial velocity. So this is an example in the velocity space of what we infer for individual stars. So these points and the error bars are individual stars, and the orange lines are the group or the cluster parameters. So we do a simultaneous inference with thousands of parameters, the stars and the cluster. So we, based on this code, this is an open and free code, let's say. We created this membership method that takes the phase space model from the cluster, and then we sample synthetic stars from this phase space model, transform to the observed space, and do the clustering in the observed space. And this give us the advantage to take into account uncertainties and the sources with missing values. So we correct for that. We create a model, a Gaussian mixture model for the field and another for the cluster. And then with that, we assign membership probabilities and do a probabilistic classification using simulated data sets for the cluster. And then we obtain the members for the group. So this is an iterative process that we use to recover the members. And I'm showing some of the particularities that the Gaia has shown for open clusters. 4 minutes. So these are, for example, these banana shapes due to geometric projections of the positions and the velocities of the clusters, of the cluster members. And then using a Gaussian mixture model allow us to take into account those distortions. This is in the observable space, and it's only a projection on some of the observables. And one of the caveats of this modeling is that it's computationally expensive in the phase space model. But thanks to GPUs, we are able to do this clustering analysis very fast in the observable space. So here are some of the results on the Coma Ver and GroupX members. So we applied this method to 45 million sources from Gaia ADR3, basically half of the northern galactic hemisphere, with only applying these proper motion cuts. There are no quality cuts. We recover more than 50% members from the previous works from Kranz and Tang, this convergent point method from Vienna, or the StarGo method. Thanks to the simulated data sets, we measure contamination rates lower than 5% and higher than 90, true positive rates or recovery rates higher than 90%. And we tackle the problem of reaching the very faint end of Gaia limit. So we identify those sources at the very bottom, thanks to this handling with the uncertainties and the missing value sources. This is just an example of the spatial distribution. So on the left, we have Coma Ver members, and these are the projections on the barycentric positions. And the tidal tails extend up to 60 parsecs from the center. And we clearly see that GroupX is composed of 2 substructures. And later on the questions, we can discuss of the feasibility of these substructures. And then we see similar stuff on the velocity distribution. Interestingly, the velocity of the tails show this S-shaped, that we still is showing us that the modeling that we are doing in the phase space still require more physical tuning. We need more complex model than just Gaussian distributions. And this is the mass distribution that we infer by combining Gaia with 2 mass and pan stars. We infer individual masses, and then we compute the mass distribution of the groups. So we see that the mass distributions are different from the Chavrier prior. This is expected for old clusters, well, old in the sense of they are not star-forming regions. And then this mass distribution show different shapes, indicating also the dynamical evolution of these groups. And this is a work in progress. So now that we have masses, positions, and velocities for individual stars, we have all the information to propagate forward in time the current positions of the individual members and try to put a constraint in the time of encounter of Coma Ver and GroupX. The previous analysis work from Kranz worked only with 61 Coma Ver members and 26 from GroupX that have fully observed phase space coordinates. Now we have more than 3 times more fully observed members, with more than 50% more members in general. And then we are expecting, we are waiting for Gaia DR3 to get more radio velocities and do the forward analysis. And then finally, these are the conclusions. Well, these interacting pairs of open clusters are interesting laboratories to study the disruption and the mixing of possible star population of these systems. What we learned in the process is that to squeeze all the juice from our Gaia data, we require to either adapt current machine learning techniques imported from other areas of knowledge, or to create our own techniques. We need to deal with uncertainties, correlations, and sources with missing values. And we need to work with parallel computing or fast computational techniques. So this is kind of an example what we need future generations to take into account the training in parallel computing to work with this and this high amount of data. And this is just the kind of I don't know, the takeaway measures is that physical forward modeling, it's complex, it's computationally expensive, but it can be an alternative to encode prior knowledge into the model and then get some updated prior and afterwards, something that is currently difficult in some pure machine learning approaches, specifically in the deep learning approaches. So that's it.
Thank you.
Thank you.
Okay, we have time briefly for one or two questions. Okay, this is the first one, and then there will be another one.
I found the non-parametric methods are interesting. They're letting it be any shape. Dynamics constrains the shape of these escaping particles that are interacting, because that's given by the combined potential of the galaxy with the clusters, plus the effect, the centrifugal potential.
Yes.
And the escaping are going to go through the Lagrangian points, which are the southern points. And then the shape they take is given by this potential. So when you compare what you are doing with different models, you can start guessing something about how the real potential is.
Exactly. That's a very interesting comment, because I think there is this theorem of not free sandwich. So where it's telling us that, okay, the non-parametric methods will be great to kind of explore possibilities of the shapes, but they are also complicated when we try to transfer or the observation that we have, the uncertainty that we have in the observable space to the physical space. So there are some caveats there. And the modeling approach, the parametric modeling approach, has also its caveats, because maybe what we are doing here by imposing these Gaussian shapes is trying to kind of biasing what we are getting by the shapes of the Gaussian. So there are other kind of pros and cons in each method. So it's interesting to apply different methodologies to get the most of them.
Do you have any way, when you are using Hamiltonian SCMC to infer those parameters, how to evaluate the precision of your predictions? Do you have any way of comparing it with already results from other data? So how do you know how far or how close are your predictions to reality?
Yeah. So for example, when we do this this Hamiltonian Monte Carlo, I didn't mention it, but this modeling is done in PyMC3, and then this is kind of an environment. And in Bayesian modeling, what we do is kind of we do the prior and predictive and the posterior predictive. So this is a way to evaluate how the influence of the prior on the posterior. And then so for example, what we do this, and this is why this part of the second version of the paper has been yet published, is because we are doing extensive validation with synthetic data. So we get in order to see that we are currently getting what we expect. So this is the part of the validation that we need to do.
Thank you.
Your analysis possible outliers?
That's a very good point. In this case, this method assumes that the list of members is unbiased. So in that case, if we are giving, for example, some binary outliers or some outliers that you are saying, that will bias the model. So what we need to do is to take care of the input list, to clean it for possible outliers in order for it to not affect the model. That's a problem with this methodology.
Okay, is there any question online? Is there any more question? Last one.
Sure,
Marta.
Just curious, but you said that you could take into account the systematics.
Yeah.
And you put it in the priors, I guess.
No, I put them in the likelihood. This is a type of model that it's a generative modeling. This is the type of models that, for example, David Hogg and Joe Bobby kind of do. So this is what we do is that to take into account the systematics, the parallax spatial correlations, what we do is the likelihood it's a Gaussian likelihood, but it's the sources are not independent of each other. So instead of treating as individual Gaussians, what we do is construct a huge matrix with all the correlations.
Well, that's helpful.
Yeah, exactly. This is helpful because in this case, the matrix is, if you have 100 stars, the matrix will be 600 by 600.
That's why everybody assumes independence.
Exactly. Yeah. Well, we can do it in this particular case because clusters, we don't have too many stars. I mean, you cannot do it for the galaxy. Yeah.
Okay. If there are no more questions, we thank our speaker again.
Thank you. Thank you.